All right, here we go. Final unit, final topic of our Calculus 1 journey, integration, which typically, or at least in my experience, is usually a fan favorite and my overall favorite concept to explore in calculus, both Calculus 1, 2, and 3. But before we get to integration, we must first talk about this idea of antiderivatives. What an antiderivative is given the derivative, you're allowed to find the function itself. So for physics-based applications, this is important because if you're given a velocity, this now allows you to determine your initial position. So let's provide a definition of an antiderivative. We say that a function, capital F of x, is an antiderivative of f of x, lowercase f of x, on AB if we take the derivative of capital F of x and we get back lowercase f of x for all x inside of the AB open set. Now, if we wanted to define this generally speaking, because this has some important graphical application, we can say, once again, this piece, right, let a function capital F of x be an antiderivative of f of x on AB. Then every other antiderivative on AB is of the form capital F of x plus c for some constant c. Now, why does this necessarily matter? Well, a quick sketch shall reveal the significance of that. Oops. So let's say we have some generic curve that represents the antiderivative. Okay. If we were arbitrarily adding or subtracting some value c, you should know from your studies in Algebra 2 that when we add or subtract, right, some value c, this is only going to, cause a vertical shift in the graph, which will not have any effect on the slopes of the tangent lines. It will simply change the location of the tangent line. Now, determining what an antiderivative is. this process is what we call integration. So if you're a calculus novice, you've probably never even seen notation. So let's get that out of the way right now. So a lot of foundational stuff, because once again we are just starting our exploration into the wonderful world of integration. So we'll get to our application soon enough, but right now we're focusing on establishing a solid framework. So the notation for when dealing with integration, right? We have our integration symbol. Right, some arbitrary function dx. This piece here, f of x dx, we call the integrand. And this is going to be equal to capital f of x plus c, right? Because if we take the derivative of this, we should get back the original function. And this entire, I guess, equation statement represents an indefinite integral. And so this is true if f prime of x, capital F prime of x, is equal to the original function. Okay. So in essence, what we're doing is we're unwinding this idea of derivative. We're going in reverse. At some point, we will learn whether or not derivatives and integration are inverse concepts. But for now, let's start small. So let's say we have, ooh, Blue, you are retired. You did not make it through the summer. Buckets. Power rule for integration. Very similar to our power rule for derivatives, but just backwards. So let's say we have some general polynomial, x to the n dx. Now with derivatives, right, we would take the exponent, we would multiply and then subtract 1. Rather than multiply, we're going to divide. Rather than subtract, we're going to add 1. Right, so we're going to add 1 to the exponent, and then we're going to divide by whatever that new exponent value is. And don't forget that we need to account for this some arbitrary c, because if we take the derivative of a constant, it is 0. Now this theorem holds true for all values of n that are not equal to -1. Now, let's prove it. Okay, so let's derive this bad boy. d dx, x to the n plus 1, or n plus 1 plus c. This piece here, right, this rational piece is going to be a constant, so I'm really just going to do the power rule on this upper function. So I'm going to take this, it's going to plop down, n plus 1 times x to the n plus 1 minus 1. The derivative of this is 0. This expression is going to simplify with this expression, and this 1 minus 1 is going to cancel, and we're left with x to the n. Ta-da! The power rule for integrals. What about if we have, I can leave that there. The antiderivative of 1 over x, because this is our situation for n equals -1. So in essence, we want to ask ourselves, if we take the derivative, what function could we take the derivative of that would get us this? So if we were to integrate 1 over x dx, that function is the natural log of x plus c. The derivative of the natural log is 1 divided by x. Okay, so once again, we are just, for antiderivatives, kind of going in reverse of this idea regarding derivatives. We have some very mundane procedural things we can do with indefinite integrals, very similar to what we can do with derivatives and limits. We have our sum rule, which says if you're integrating the sum of two functions, you can integrate them separately. And if we have the multiple rule, this means that we are multiplying the function by some scalar value, which we can once again remove. This is probably the most convenient at times when you get deep into integration. Let's try one practice problem before we outline some other foundational knowledge and delve a little bit deeper into this chapter. So let's say that we had something along the lines of evaluate the integral of 3x to the fourth plus 5x to the 2/3 plus x to the negative 3 dx. Okay. Once again, what we want to do is we want to reverse derive these, anti-derive them. So we're going to add 1 to all of our exponent values. But let's start slow and steady. So if I add 1 to 4, I get x to the 5th, but I must divide by that value, and the constant remains. Right? Because right now I'm applying this scalar multiple law we just wrote down. Same thing holds here. X to the plus 1, so we're going to have 5/3. But when we divide, it's the same thing as multiplying by the reciprocal. So it's really 3/5, right, times 5, but those will cancel. And last but not least, if I add 1 to this, I get x to the negative second power. I'm going to divide by, and I'm not going to forget to change my sign. And then as always, you can't forget about c, because remember c is just adjusting the vertical height or the vertical position of the antiderivative and nothing less, nothing more. I need a little bit of room. Let's get rid of this. Just to make sure that we have it in our notes, our basic trig integrals. Remember, we're just reverse engineering our derivatives. So we'd ask ourselves, well, the derivative of what function gives the sine of x? Well, it's negative cosine of x plus c. The derivative of what function gives us cosine x? That one's even easier, sine of x plus c. The derivative of what function gives us secant squared x? That's easy, tangent x plus c. The integral of, or the derivative of what function gives us secant x tangent x? Secant x plus c. The integral of cosecant squared is equal to negative cotangent x plus c. And the integral right, so if we take the derivative of any of these functions, it will yield us whatever is in our integrand. There are some general rules that we can write down, but I'd rather not, because then you just kind of get into this formulaic recall process rather than, you know, a foundational conceptual understanding. So if you want to take a look at those are located in your textbook. And we can do the practice problem with one. Sine of 8t minus 3 dt. Okay, we have a little bit of complexity here. Oops. Plus 20 cosine of 9t dt. Right, so if I were to reverse engineer this, right, I'm asking myself, well, what function when I derive will give me sine? That's easy, cosine, negative. The input will obviously say, but if I were to derive this, I would have to derive that. So that would give me an 8 outside as a coefficient, so I would need to make sure that I divide by 8. Therefore, when I derive this, I'll be left with this original function. And very similar idea here, plus 20 sine of 9t but when I derive sine, this 9 will once again pop out. So I want to make sure that I account for that in my integration. And that shall do it. Last but not least, we can talk about our basic exponential integrals, which say what function, when I derive it, will give us e to the x. Well, I love when this happens. It's just e to the x. Okay. And then if we have something more general, right, that looks something like this. Right, we keep the original function, but we'd be mindful that we need to divide by that constant that's attached to the variable, and vice versa. Just like we saw with our trig integration, if we were to derive 12 times e to the 7 minus 3x, I would just need to make sure that I divide by this 12 divided by negative 3, e to the 7 minus 3x. Right, because if I were to derive this currently, this function stays as we see it here. The 12 is still there, but I would have to derive this exponent. This is going to be a 0. This will yield a negative 3 that I need to simplify out because that is not included in our solution here. So if we really wanted to make sure that we had a simplified answer, we could do it as such. Okay. This unit is going to have a lot of practice in it, so I strongly encourage you to pause the video when a problem is presented and try to work your way through it. That way I can kind of walk you through the reasoning and the rationale if you are to get stuck. But that's where we're going to pause, and we're going to pick up in the next video with the definite integral. See you there.